Right, now just a reminder of what we did in another previous session. For a nicely shaped distribution that's unimodal, it's not too badly skewed, it doesn't have overly long or overly short tails, we usually expect to find these results. Within one standard deviation of the mean, we will have 68% of the data. We'll see here, 68%. Well, approximately 68%. Within two standard deviations from the mean, okay, two standard deviations from the mean, we'll find a total of approximately 95% of the data, and within three standard deviations of the mean, we'll find approximately 99.7% of the data. Now these are approximations because we haven't been really all that strict in our conditions for the shape of the distribution. We simply said unimodal, not too skewed, and the tails mustn't be too long or too short. So we haven't given really specific criteria. So these percentages are approximations, and we call this property the empirical rule. This is what we looked at in a previous session. Okay, so this was just a reminder. Now, let's consider a continuous random variable x. Okay, so when you think of continuous, then it means uncountable many possible outcomes. If you think of a continuous random variable, then it's all possible outcomes because a random variable represents a population, and capital X is just the name that that distribution has. So if we think of a continuous random variable, we'll call it x. If it is bell-shaped, do you know how bell-shaped looks? It looks like that, almost. If it's unimodal, so bell-shaped and unimodal, which means one peak only. And if it is symmetric about the mean, so if it's unimodal, symmetric, and the mean is in the middle, so if we draw it, then that's going to be the place of the mean. And it follows the empirical rule, then we can say that x is a normal random variable with parameters mu and sigma squared. Now let's see what that means. We'll denote it by a capital X with this wave, or this tilde sign, capital N, which means normally distributed or normal random variable, and remember in brackets we always have to give the parameters because the parameters are the population values that determine how this distribution looks, right? So how the curve looks. Now we see here that this part in the green brackets, this is our PDA for probability density function. Now it looks a bit intimidating, but we're not going to be working with this. Like I said earlier on, we're going to be looking at using cumulative probability tables in order to calculate our probabilities. So the only calculations we must be able to do is the normal operations, multiplication, division, addition, and subtraction. Right, and then in the case of our normal random variable, x can be absolutely any value. Okay, so it can be anything on the real line. The expected value of x, which is our mean, that'll be equal to mu. So this parameter that we talk about, mu, this parameter mu, that's the average of x, or the expected value of x. And sigma squared, which is this sigma squared, is the variance of x. So in other words, this mu, which is the mean, or the expected value, tells us where the distribution is located, because the mean is a measure of location. And then the variance, the sigma squared, tells us the size, because this variance is a measure of spread. Right, now this normal distribution, which is bell-shaped, unimodal, and symmetric about the mean, it is actually the nice distribution that the empirical rule refers to. Okay, so the empirical rule, when it talks about a nice distribution that has one peak and fairly symmetrical and so forth, it actually describes the normal distribution. This is the one that you should be thinking of, bell-shaped, unimodal, and symmetric about the mean. Right, so graphically this is how it looks, and the properties that it has, it says here that it's symmetric about the mean. So that means that the mean is in the middle over here. Okay, remember this is our x-axis. The mean is sitting right here in the middle. All the other values are to the side of the mean, but it's a 50-50 split. Okay, because it's symmetric about the mean. So we have just as many values below the mean as we have above. It's also spread in the same way below the mean as it is spread above the mean. That's why this half of the peak looks the same as that half of the peak, and it's 50-50. And because of that, we also say that the median is equal to the mean, which is equal to the mode. The mode is a value that occurs the most, so obviously it's going to be in the middle, highest peak, which is also the mean, which is also the median, because the median is exactly the middle of the distribution. Right, now when it comes to the probabilities, then the same applies as what was mentioned in the case of general continuous random variables. We'll integrate from one point A to another point B, and the result of that integral over here, that's going to be the probability of being between A and B. In other words, it's the area under the curve. That's the probability. Right, now let's look at this property, symmetric about the mean, or symmetry about the mean. What does it mean? Well, if we have our distribution, which is bell-shaped, right, our normal distribution, and we take mu, which is the middle point, and we subtract a value. Let's say in this case, the value is some other constant c. So when we subtract it, and then we take that same quantity and we add it to the mean, then what we're actually saying is that the probability of being less than this value over here, in other words, this area over here, is the same as this area over here, which is the probability of being greater than mu plus this value. And by the same reasoning, the probability of being less than this, so this area over here, is the same as being the probability of being greater than this. Okay, so that's what the symmetry part means. Whether we're on the left or on the right, the probabilities will be the same. Right, let's see the effect of the parameters mu and sigma squared. Now I said, and we saw also from a previous session, that mu is a measure of location, so it tells us where the distribution is situated, or where most of the data is situated. Sigma squared is the spread, so it tells us the size of the distribution, how much it's spread out over the axes. Right, so if we consider these three normal distributions, and I'm saying that there are three normal distributions because each one of them is bell-shaped. They just look slightly different because the one is flat and the most extreme one is flat and wide, whereas the other most extreme one is again narrow and very tall. Remember, the area under the curve must be equal to 1. So if we have a very high distribution, it means that it must be very narrow. If we have a very low distribution, it means it must be very wide, just so that the total area under the curve is equal to 1. So each one of these has a normal distribution, but if we look at the parameters, then we see that the three means will be the same, okay? Because all three of these are situated along the same middle point. However, the three variances are not the same. We can actually see here that the variance for x2 is the largest. So the variance for x2 is the largest. The next variance will be the variance for x1. So the one that's just smaller than that will be the variance for x1, and the one that has the smallest variance will be x3, which is the blue curve, and that'll be sigma 3 squared. Yeah, so three different variances, but the same mean. Now, if we have a look at these three, then we see again that they're all three normally distributed. They have three different means in this case. Clearly, mu1 is less than mu2, which is less than mu3, okay, because there are three different locations on the x-axis, and of course this x-axis is a number line. Smallest value is on the left, largest value is on the right. So mu1 is the smallest. But what can we say about the variances? Well, we can say that all three of them seem to be the same. So even though the curves are on different locations, all three of the variances are the same. Right, so if we look at what it means regarding probability, then if I were to take mu1 and add a value to it, let's say c, then I might get a point over there. And then that area over there will be a probability. Now if I take mu3 and I add the same value c to it, I'm going to get a point over there, which will give me a probability to the right, which is equal to that. So then that probability will be the same as that one. If I take mu2 and I subtract a value c from it, I'm going to get a value over there, and if I look at the probability of being less than that value, then by symmetry it's going to be the same as these two that's actually on the right hand side. Okay, so that's what this result over here on the right hand side said, okay, the symmetry property. This is exactly it. Of course, When the variances are different, then this is not going to be true. Okay, this will only be true when the variances are the same. And we can see that because if I take this mu over here and I add a constant c to it, I might get a value that's sitting over there. So if I take a cutoff point and I look at the area under the curve on the right hand side, we can see that the probability for x2 is much greater than the probability for x1, because that's just a small area over here, and x3 doesn't seem like it's going to have any area at all. It seems like x3 actually ends over here, because from there onwards it seems to be 0. Okay, so clearly three very different probabilities for the same cutoff point on our x. Let's consider a random variable. We'll call it x, and we'll say that x is normally distributed with parameters mu and sigma squared. So that means that if we were to plot the distribution, then it's going to be bell-shaped, unimodal, and symmetrical about the mean. In other words, the mean of the data set is going to be in the middle. Of course, we're working on the real line, which will be our x-axis, and the symmetry means that we have 50% of the data to the left and 50% to the right. Now please note that the area over here on the left and this area on the right represents 50%, but the actual data is over here on the real line, right on the x-axis. So that's where we have the actual data. Right, now the next step, we'll calculate all possible z-scores. So that means we will take each and every single x value that we have on our real line or on our data set. We'll subtract the mean from it, which is mu, and we'll divide by sigma, which is our standard deviation. So this subscript I over here, that just refers to all possible x values and all possible z values. So we can make I equal to 1, so that means we'll calculate the z-score for x1. When we make I equal to 2, it means we calculate the z-score for x2. So we simply calculate the z-score for each and every single x value. Now, next step. If we take all of those z-scores and we want to plot it, what's going to happen? Now let's say that this is the plot for the z-scores. And of course here you'll see our number line now is not our x-axis anymore, because we don't have the original data sets, right? We don't have the original x's anymore. We're now plotting the z-scores. So this axis here, the horizontal axis, will be our z-scores. Now let's see. In the middle of this we will have our average, which is 0. Now why is the mean of the z-score 0? Well, let's see. The first z-score will be the smallest x value minus mu. Now that difference is going to be negative because x1 will be less than mu. So if we take the z-scores for all the x values less than mu, then all of those z-scores will be negative. If we calculate the z-scores for all the x values greater than mu, then all of those z-scores will be positive. And it so happens that when we want to calculate the average z-score and we add all of these negative z-scores with the positive z-scores, the answer is 0. So if we have a total of 0 and we divide by the number of values that we added, which is n, then the answer will of course be 0. So that's why the middle point of our z-scores will be 0. Now, to the left of 0 we have 50% of the data, and to the right of 0 we have the other 50% of the data. Now when I say data, I actually mean the z-scores of the data. And the reason for this is because below mu we have 50% of the actual data, and above mu we have the other 50%. So this means that in terms of z-scores, below 0 we will have 50%, and above 0 we will have 50%. Now it actually works out that our z-scores, when we plot it, the z-scores have a normal distribution. That's why it's bell-shaped, unimodal, and symmetrical. And the parameters for the z-scores are 0 and 1. In other words, the mean is 0 and the standard deviation is 1. Right, so more formally, we have our z-scores, which will be real numbers. In other words, anything on the number line. The expected value of z will be 0, in other words the average is 0, and the variance will be equal to 1. Now let's look at the properties of our z-scores. And it so happens that the z-scores share the properties of the distribution of x. So x is normally distributed, so that means that the z-scores will have all of those properties. So let's say, for example, we choose any x value here on the x-axis, and we indicate it with this red line. Then if we're interested in the probability of being less than x, then we will calculate this area over here. We'll determine this area, and that will be the probability. Now if we calculate the z-score for that specific x value, so in other words, if we take x1 and we subtract the mean from it, and we divide by the standard deviation, then we'll get z1, which is the z-score for x1, and we indicate it on our z-score distribution. Then the area to the left of the z-score will be the same as the area to the left of x. And this is actually a property that we've been using when we calculate probabilities for normal random variables. Right, but this is now a little bit more formal than what we had before. So the probability of being less than our x value is the same as being less than the z-score. So that's why it doesn't matter what normal distribution we have, right, what parameters we have. When we convert to z-scores, in other words standard deviations, counting standard deviations, then we can use our standard normal table. And that is why our z is referred to as the standard normal distribution. You'll see in the heading here, I've added the word standard. Okay, so z will be our standard normal random variable. Right, and then just to conclude, symmetry properties of z are really important, so you should be familiar with it. Probability of being less than 0 is the same as being greater than 0, so that'll be a half. Remember, that means it's x greater than mu is the same as x being less than mu when x is normally distributed. If we take any negative value, then probability of being less than that will be the same as the probability of being greater than the positive version of that value. If we take the probability of being greater than any negative value, then of course by symmetry it will be the same as the probability of being less than the positive version of that value.